Our next problem concerns a two-unit system, a two-element system in series. So there are two cables hanging from the ceiling, subjected to a point load P, and let's see how we set the problem up. In terms of the mechanical behavior of the units or the elements, they could be ductile on the one extreme or brittle on the other extreme. But it so happens that when you have a series system like that, it makes no difference to the failure domain, as we will see. So the failure is defined as the strength of the first element R1 less than P, or that's the union sign, R2, the strength of the second element, is less than P. Both of them are connected in series. It's a very simple system, so both of them are carrying the same load, P. In terms of the failure domain on the R1, R2 space, we see that it's quite a large area that corresponds to failure. It's the union of the two regions, R1 less than P and R2 less than P. Now, whether the materials were brittle or ductile would make no difference, because for brittle it would fail and immediately the system would collapse if any of the elements failed. And if any of the elements started to flow, if they were ductile, it would lead to the same problem, that there would be an unstable flow in the system. When these two units are connected in parallel, things become a little more interesting, and the behavior, the mechanical properties of the materials, that actually starts to matter. So let's take a look at that. So we have now a parallel system, and later we'll see that this arrangement is called an active parallel system. So you have the load P, R1 and R2 are connected in parallel. It's not necessary that the load be shared equally between the two elements. Let's say the loads are shared as in terms of alpha and 1 minus alpha ratio. So R1 carries alpha P and R2 carries 1 minus alpha P. So what would be the failure domain or the failure set when the behavior is brittle? We actually can look at it from a sequence of failures. So if R1, if the first element were to fail first, it would mean that it is not able to carry alpha P, but R2 is able to carry 1 minus alpha P. So the region marked 1 on the right, that rectangle, would be the sequence, would correspond to the sequence that 1 fails first and then 2 fails, because when 1 has failed in a brittle manner, then the entire load is now carried by 2, and if it had to fail, then R2 is less than P. So R2 is greater than 1 minus alpha P because it failed second, but it was not able to carry the entire load, so it is less than P. So that defines my rectangle 1. Likewise, I can define my rectangle 2, which indicates item 2 or element 2 fails first, and then element 1 fails. So element 2 is now less than 1 minus alpha P, whereas 1 is greater than alpha P. It's able to carry its load in the intact condition, but it is not able to carry when it is asked to bear the load by itself. Now what about the rectangle in the middle, the one that I've marked with 3? That's interesting. That basically says that it is that combination where neither of them is able to carry the load assigned to them in the intact condition. So R1 is less than alpha p and R2 is less than 1 minus alpha p simultaneously. So together those three regions define the failure region in the brittle case. And so once I am able to set the problem up, I can then undertake probability computations and find out failure probability and so on. But this would be an important step in the reliability analysis. What would happen if the materials behaved in a completely ductile manner? So here the failure region becomes smaller because even when one element fails, when the first element fails, it does not give up all the load. It's able to carry the load at which it yielded. So failure for a ductile element is plastic flow. So even if it failed, it is able to carry the load at which it failed. So the other element needs to carry the difference. So if you do the math, you can see that the failure region now becomes a triangle. So my ability to set the problem up leads me to this situation where I can now compute the failure probability or the reliability of the system.